Hi, I'm Sam Wong. This is Lab 2 for Physics 2211, and we're looking at falling objects today. The purpose of this lab is to be looking at Newton's second law as it pertains to multiple forces and also drag force. So Newton's second law, as we explained last lab, is the force on an object that's equal to its mass times acceleration, which brings on these equations, F equals ma, F net equals the change in momentum, and also velocity equals initial velocity plus F net over mass times delta t. We're actually going to focus on F net over mass today because we're looking at multiple forces. So in this experiment, we'll actually be observing the gravitational force, which is mass times gravity when we're near Earth, so it's 9.8 meters per second for the acceleration, and then drag force, which is coefficient of drag times the area of an object times the density of the liquid, which is our air, velocity squared divided by 2. This is important to study because it shows that Newton's second law is actually very accurate in situations with multiple forces, and also it is very good to understand this, specifically if you're in aerospace engineering or you just want to go skydiving, because you have to understand how objects reach a terminal velocity due to drag force. So this is the experiment we're doing today. I use a sock as my object today, and it had a mass of 0.34 kilograms, area of 0.0184 meters, and the distance I dropped it from was about 5 feet, which is 1.53 meters, and it fell at an observed time of 0.643 seconds. And we can show you the video right now in lab. So here we are starting off. The object, as you can see throughout the video, you can see that the actual distance between each frame gets larger as you go along, which will be explained in the next slide on my prediction model. So for this experiment, we used two different prediction models. First, we looked at the gravitational model, which only takes into account the force of gravity. So in Newton's second law equation, we plugged in F net to be mass times the gravity of Earth, and we'll show you that a little bit. The next model we used was the drag force model, which again, we used Newton's second law equation, but we had multiple forces to make F net. So here we have the gravity force plus the drag force. For drag force, here's the equation we already looked at. And for the coefficient of drag, we used 2.1 because the sock I used was shaped for the most part as a rectangular container, so I used 2.1 as the coefficient, and then the density of the air I found to be 1.225 kilograms per meters cubed. So let's look at the models I used. First up, this is the gravitational model. You can see the mass is here, but there's no initial velocity and there's no drag force here. And we'll run this. So here you can see the ball goes down and the velocity increases at a constant clip. And then this is my drag force model. So as you can see here, we have the values for the constants of the drag force, and then we have it added together here to create the F net. So let's run this program. And as you can see, this is no longer a straight line, it is curved, and that's because of the drag force. So from my prediction models, I actually got a resulting graph. Here we are, the y position of the sock versus time. The blue dots represent the observed position of the sock in the video. The red dots are the gravity model predicted position dots, and the yellow dots are the drag model predicted position dots. So as you can see right here, the drag and the gravity models are very close in the beginning, but at the end, the drag model is a lot closer to the actual observed position of the sock, while the gravity model is a lot further away, and that's because the drag model takes into account all of the forces that are acting on the sock, while the gravity only takes in gravity. With these results, we actually have some discrepancies in my own experiment. The first one being the sock actually started in a convex shape, which is right here because I was holding in a point in the middle. This could actually increase the amount of initial air drag on the sock, thus slowing it down in actual life a lot more than what should have happened. So you can see this discrepancy right here as both of the models have predicted positions a lot lower than what the actual observed position of the sock is. That could be a reason. Another reason for that could also be the unknown constants for drag. So I actually just used a rectangular container as my coefficient for drag because I didn't know the actual coefficient of drag for socks were. And also we don't know the actual air density that is inside of my house. So there could be a lot of things that affected the sock to be a lot slower than what it actually was predicted to be. Despite these discrepancies, I can actually tell you what it means. It means that you can finally calculate and understand what terminal velocity is. Terminal velocity is when the net force on an object is actually 0 newtons, thus that object has a constant velocity according to Newton's second law equation. The net force reaches 0 when the drag force is actually lifting the object that is falling at the same rate the gravitational force is pulling the object down. This can be seen in our prediction models. So here's the gravitational prediction model. You can see that the velocity is constantly increasing over the whole entire fall. But when we add drag force, like we have above here, the drag force actually balances out the gravitational force at about 1 second. Thus it has a constant velocity of about negative 3.75 meters per second. Now you're probably thinking that's cool and all, but what if I just wanted to throw the sock? Throw it as hard as I could towards the earth and not just drop it? Would it reach a terminal velocity? And what time would it even reach it? Actually, it would reach in the same exact time as you just dropping it. And that's because the drag force is proportional to the velocity squared. So the harder you initially throw it down, the harder the initial drag force is. Therefore, it would bounce out in the same exact time. You can see this in the two different computational models that I actually did. So here we have the first one where you throw it at -2 meters per second, which is still less than the terminal velocity of the object. and it reached terminal velocity at about 1 second. And then here we have me throwing it harder than the terminal velocity at negative 10 meters per second, and it still reached the terminal velocity in 1 second, which is amazing to observe. It actually explains the parachute zone for skydiving. So despite not knowing anybody's weight, height, or anything, skydivers know that there's a time period in which you need to put out your chute so that you will land safely and reach that terminal velocity so that you won't hurt yourself. It's actually very important to know this physics, and that's actually another example of why you should learn about drag force.